Worksheet problems for Chapter 6. The first problem, we have a car going around a banked curve, and we're asked to find the minimum and maximum speeds where it can safely do this. So the concepts here, we have something about friction. We're going in a circle. If we're going in a circle, we know we're going to have a certain acceleration to stay in a circle. And we call that the centripetal acceleration. So I should have put centripetal first. And what are the things that keep it from sliding and make it accelerate? Those are forces. So we'll have Newton's second law. Now draw two sketches of the problem, one with the top-down view and the other looking at the tail end. And then on the tail end view, draw the forces for your free body diagram. So here's my two views. The top view, you have the car going around here. If I drew the forces, I would have the force toward the, you can't really break it up. It just doesn't work. This one here is the one that works. But this is important to get the picture of, hey, it's got a radius of 60 going around the circle. This one here, I can draw the forces. I have the force gravity, which by definition is acting downward. Actually, let me put that above. And technically, it's acting on the center of mass of the car, something that's going to come up in the coming chapters. Then I have the force normal that's acting normal to the surface. And you'll see from my wiggly line there, force normal is nowhere close to vertical in this case because of that 45-degree angle. And then I have the force of friction. Now, the force of friction could be going up or down depending on what it's doing. And so I'm going to draw the force of friction going the direction it would be if the car was not moving. Right, if the car is not moving, it's going to want to slide down, so I drew it going up. So there I've drawn the forces. And so, hey, that's only three forces. Huzzah! Put those in here. I have the force of gravity, the force normal, and the force of friction. Force of gravity, force normal, and the force of friction. Ah, the joys. If I'm going to put them in that table, I need to break them into components. And first, I need to choose a coordinate system. Now, what was the first rule? The first rule for the coordinate system is if you have an acceleration, make that one of your coordinate directions. I have an acceleration here. The acceleration is going this direction because it has a circle, a centripetal acceleration. And so I'm going to choose my directions. So I have, this is my centripetal direction, and this is my y direction. So I didn't use x and y, I used centripetal and y. This way I don't break my right-hand coordinate system. So I need to break these into components, and notice the force of gravity is already broken into components. Don't need to worry about that. But I need to break both the force of friction and the force normal into their components. Now in this case, I chose 45 degrees, which is actually a poor choice by me, but it's a poor choice because it allows you to make mistakes and still get it right. So let's look at breaking those forces into components. So here's my force of friction. And my component directions are this and this. Now the question is, which angle do I know? I know this angle. And so the force of friction in the x direction, force of friction in the y direction. The adjacent side is the force of friction in the x. So cosine theta is equal to the adjacent force of friction x over the hypotenuse force of friction. Therefore, the force of friction in the x direction is equal to the force of friction times cosine theta. And likewise, sine theta is opposite side, which is force of friction y, over hypotenuse force of friction. So force of friction y is equal to force of friction sine theta. That's breaking one of my forces into components. Breaking the next one, the normal force is like this. And so break that into components. My components are, that's not much contrast in color now, is it? There's a better color contrast, I think. So once again, if you start the tail, you go like this and like this. And now we have to decide what angle we know. In the case of friction, it was easy because we had the slope and the horizontal, and theta was defined by the slope and the horizontal. But for the normal, I have the normal, which is perpendicular to the slope, and vertical, so this angle here is theta. And I should put C's, not X's. C. C. So here, I would have force normal y is the adjacent side, so cosine theta equals force normal y over normal. Therefore, force normal y is equal to normal cosine theta. Sine theta is equal to force normal x, the opposite side, over normal. Therefore, force normal x is equal to normal sine theta. Now, my arrows have directions. Notice force normal c, I think, yes, I used x again instead of c, is pointing the same direction as my c was in my direction. So that's a positive and a positive for the y. So the normal was positive in both. The friction was going opposite the center, so it's negative in the x, but positive in the y. So when I break these into components, my force of gravity, it was already 0 and minus mg for the y direction. The force normal in the central was, and so now we come here, it was positive because it's going toward the center, and it's n sine theta. And in the y direction, it was also positive and cosine theta. And finally, the force of friction in the central direction, it was negative. I'll put mu n because that's what the force of friction is, cosine of theta. And the y direction, it was positive mu n sine theta. So remember, I substituted mu n for the force friction there. So there I have all of my forces. Well, why do we do this? Why do we do anything? So we can find answers. What is the equation for the acceleration of the car if it does not slip and travels at constant speed around the corner A? Now, notice again, I put the force of friction with an equality. Really, the force of friction is less than or equal to mu n. But here I put the limiting case where the force of friction is equal to mu n. So in that case, if I want to find the acceleration, then there's the equation of acceleration. V squared over r is the equation for the centripetal acceleration every time. I didn't have to use Newton's second law for this. That is what is required for the car to go around the corner. Now, if I apply Newton's second law in the vertical direction, I can get adding those up, minus mg plus n cosine theta plus mu n sine theta equals 0. Wow, that's kind of rough, right? But if I solve that for n, I'll have mg is equal to n times cosine theta plus mu sine theta. So n is equal to mg over cosine theta plus mu sine theta. So there I have the equation. And We actually know what m and g are, and we know what mu is, and we know what theta is, so we know everything there. We can get a value for that. Now use Newton's second law in the centripetal direction to find the equation for the minimum speed to stay on the turn. As minimum speed, remember I drew my direction as if it was stopped, so minimum speed is going to have the force of friction in the same direction. And so using the horizontal, or the central direction, I did say central, didn't I? Using the central direction, I have some of the forces in the central direction. It's MAC, which gives me, adding those up, n sine theta minus mu n cosine theta equals mv squared over r. Well, I just solved for n, right? And so if I substitute in n and then solve for v, and I have to come over to the side because I ran out of space there clearly. So that's n sine theta minus mu n cosine theta equals mv squared over r. Just make sure I copied it right. Then I have there, I just factor out the n. Now I'm going to substitute for n what we just found. So they're substituting for n. The beauty of m. M cancels. This by divide this by n. Divide this by n. Those cancel. Those cancel. I still have to multiply everything by r. And now I have an equation switching sides. V squared equals rg times sine theta minus mu cosine theta over cosine theta plus mu sine theta. So I have an equation for my speed. Now with that equation for my speed, I just go ahead and calculate it. So I square root both sides. And I have v is equal to plus or minus the square root of rg sine of theta minus mu cosine of theta over cosine of theta plus mu sine theta. Put in values, that's equal to the square root of 60.0 meters times 9.80 meters per second squared. Sine of 45 degrees minus mu. Mu is 0.850. Cosine of 45 degrees over cosine of 45 degrees plus 0.850 sine of 45 degrees. The joy. If you put all those numbers, now notice it's a plus or minus, but we don't care if you're going forward on the turn or backward on the turn, so we're just going to take that magnitude. If you put all the numbers in, according to my calculations, that gives you a speed of 6.9, and how much should I have here? Probably should have one there. 6.91 meters per second is the minimum speed. So we had the equation, v min was equal to square root of rg times sine. Okay, so it was that. And then when we put in the values, we got 6.91 meters per second. Now, change your force of friction direction to find the maximum speed at which the car can make the turn without sliding. So what this is going to do is going to come back here and change the signs of those two. So minus plus and plus minus. So if we change those signs, then ultimately every term that has a mu with it is going to have the sign reversed. So I can jump right to the quick of it by recognizing that it's going to change the signs of these two terms. So this was V min. If I do V max, it's going to be that. So putting my numbers into that equation, I don't know where, here's the V max. So I have that's down here. And putting the numbers in, that gives me 85.2 meters per second for the maximum speed. Now I did skip one step, applying Newton's second law of the vertical direction to find the equation for the normal force acting on the car, Fn. I actually didn't say to do that above because, of course, I didn't think it through. But before, it was mg over cosine theta plus mu sine theta. Because we changed the direction, it's going to be over cosine theta minus mu sine theta. So it's going to be oh wait, I did do it. I had it right there. All right. Note you never actually used the mass of the car anywhere in these calculations. We didn't calculate the number for the normal force, or else you would have had to use the m. But to calculate the maximum minimum speeds to make the turn safely, the mass didn't matter. So you could be racing a really light car or a really heavy car. It's going to have the same minimum and maximum speed to stay on this heavily banked turn. All right, that ends this problem, and it's time to move on to the next one. A wheel of radius 0.58 meters starts from rest and begins rotating with a constant angular acceleration. At time 0.82 seconds, it is rotating at omega final is 9.5 revolutions per minute. Find the angular acceleration along with tangential acceleration and final total acceleration for a point on the edge of the wheel. The concept is, and there's really two concepts because of the last step. The first one is just rotational kinematic equations. We're just going to use kinematic equations. But then for the second part, we're going to have to do centripetal acceleration. Because when it asks for the total acceleration, we have to include all kinds of accelerations. So the first step, convert. Now, it doesn't say to draw a picture. I have to draw a picture. Here's my wheel. We have omega initial, or the subscript is 0. It's 0, right? Because it's not rotating initially. It says it starts from rest. It doesn't say omega 0 is 0. It just says it starts from rest. And then we have omega final is equal to 9.5 revolutions per minute. And so I'm going to draw a little arrow here for rotating. And it tells us we have a radius. It tells us the radius. A radius of 0.58 meters. And we have delta t is equal to 0.82 seconds. And those are all our numbers. So now that I have my problem written out, I can do the first thing. Revolutions per minute to radians per second. Remember, conversion factors always have a value of 1. First, revolution. So I'm going to have revolution on the bottom to cancel the revolution on top. Well, one revolution is 2 pi radians, right? One circle has 2 pi radians in it. So that's my conversion factor between revolutions and radians. And then I had per minute, so minutes are on bottom, so I need minutes on top to cancel. And seconds are the standard units, so 1 minute has 60 seconds as my second conversion factor. So I take that 9.5 revolutions per minute, multiply it by 2 pi, divide by 60, and it gives me 0.994838 radians per second. Now, why did I keep all those ridiculous units? Well, because that way I won't have a round off there stinging me in the future. To significant digits, that's only 0.99. So I put 0.99 here because that's the significant digits, but I need to keep them all for future calculations. Use the appropriate kinematic equation to relate angular velocity and angular acceleration and solve for angular acceleration. So we learned before from linear that what we have is speed, time, and we're looking for acceleration. We don't care about position, so we use the equation without position, which was v final equals v initial plus acceleration multiplied by time. Converting that to angular, you just replace v's with omegas and a's with alphas, and you have omega final equals omega initial plus alpha t. So I'm looking for alpha, omega final minus omega initial over t equals alpha equals 0.994838 rads per second minus 0 divided by 0.82 seconds. And so just popping that in the old calculator, you get 1.213 radians per second squared. So 1.2 to appropriate significant digits. Convert the angular acceleration to tangential acceleration. So now it's asking, what is the acceleration of a point on my wheel? And so acceleration tangential is equal to angular acceleration just multiplied by radius. So that's 1.213 radians per second multiplied by my radius of 0.58 meters. And that gives me 0.7037 meters per second squared. Two significant digits, 0.70 meters per second squared. But now I have to get the centripetal acceleration. So centripetal acceleration is, now what I used in the last problem was v squared over r, but that's also equal to omega squared times r. So that's going to be my omega final which was 0.994838 rads per second, quantity squared, times the radius 0.58 meters. And so that gives me a final centripetal acceleration of 0.5740 meters per second squared. And now to find the final, I have the tangential acceleration is going like that. The centripetal acceleration is going toward the center. And so those are perpendicular to each other. Tangential and central are perpendicular. And so my A, and I'm going to call here A final, is going to be just using the Pythagorean theorem from adding those two. Square root of A tangential squared plus A, nice job, that's a C, C squared equals the square root of A tangential, 0.7037 meters per second squared, quantity squared, plus centripetal, 0.5740 meters per second squared, quantity squared. And that gives me a final acceleration of 0.9081 meters per second squared, or 0.91 to correct significance, meters per second squared. So this second problem was just strictly using rotational kinematic equations and once again having to use the idea of centripetal acceleration. All right, hopefully this has you more ready for the exam.